Okay, thanks. It's a pleasure to be here, and thank you for inviting me. So far this week, we've had some wonderful talks where we've seen quite a lot about the Berkovich analytification of a space X, and we've seen at least a little bit about tropicalizations, and then we've been seeing some hints and suggestions and a few concrete details about how these two things are intimately related. And so what I'm going to do in this talk is really dive deeper into those relationships between the analytification and tropicalizations, and hopefully say something interesting. So to start with, I'm going to be working over K, a non-Archimedean field, which means it comes with a valuation, which goes from K to the tropical numbers. I'm an optimist, so I'll use the max plus convention. This is the reals with a negative infinity. But I'm going to get to some point where that convention becomes invisible, and you don't have to worry about it anymore. One of the things I want to emphasize is that we're all used to treating things like fields algebraically. And I want to really emphasize that we should treat the other side of this valuation on equal footing. And I want to do some semi-algebraic geometry. I want to do algebraic geometry over that semi-ring. And I'll come back to, towards the end, showing you how this actually helps illustrate something about the structure of the Berkovich analytification. Okay, so we have our field. We have a scheme over K. And now associated to X, we have the analytification. And this is the Berkovich analytification. Which we've seen before, but just to remind you, in the affine case, if this is spec of some K algebra A, then the analytification is valuations W on this algebra A, extending the valuation on the ground field. And if X is not affine, then you can glue these affine patches together in a fairly easy way. I'm going to pretty much stick to the affine case all the way through this talk, because the gluing is not really essential to this story. It's easy to globalize everything I say. Okay, so the Berkovich analytification is something intrinsic. Given X, you've got an analytification, and it doesn't depend on any choices. On the other hand, the Berkovich analytification, as we've seen in some of these pictures, is this horribly infinite, huge, fuzzy, fractal-like thing, and it's a little bit hard to get our hands on it. So at the other end, we've seen tropicalizations are nice, finite polyhedral type objects, and in a topological sense, they're much easier to work with. But they depend on a choice. So if I have X and I choose an embedding into a toric variety, then I get a tropicalization, and I'll write it this way, the tropicalization of X inside Z. And just to establish some notation, let me tell you how I think about this. We'll do the affine case, where Z is given by, so if Z is given by spec of some affine toric monoid, if Z is an affine toric variety, it's given by spec of K adjoins some nice toric monoid here. And X is given by some ideal I inside there. Then, first of all, I'll describe tropicalization as a two-step process. First of all, we can take this ideal inside K adjoin M. This is, in particular, it's a linear subspace of this vector space here. And I can tropicalize that linear subspace. It might be infinite dimensional, but I'm not going to worry about that too much. So we then get the tropicalization of I in the linear sense I know this definition is a little bit circular, but you've already seen tropicalization, so I hope you'll forgive me. We get the tropicalization of I, which is a tropical linear subspace inside T adjoin M. Now this is an algebra over T, and this thing in here happens to be an ideal. It's not just any ideal. It happens to be an ideal which is made out of, which is also a tropical linear space. And in Diane's talk, she's going to tell you much more about these particular interesting matroidal ideals, or these tropical linear space ideals. But for now, I want to use this to tell you how to describe the tropicalization of X. So the tropicalization of X in this affine case is then the intersection over all G in the tropicalization of the defining ideal of the tropical hypersurface associated to G where V trop of G is the set of multiplicative maps, I'll call it P, from the monoid M into the tropical numbers, viewed as a multiplicative monoid, forgetting the additive structure, such that, let's see, such that if we write G as, if I write G as a sum of lambda I times elements xi, where the lambda I are elements of T, and the xi are elements of M, then the sum of the lambda I times P of xi. So this is a sum of a bunch of tropical numbers, and of course tropical sum means max. This is a sum of a bunch of tropical numbers here. The maximum is attained twice. The maximum is attained at least twice. And if there's only one term in there, then I also have to allow the possibility that the term is actually negative infinity. So maybe more accurately, I should say it tropically vanishes. So this tropicalization, it sits inside Hom in the category of monoids from M into T. So if M is something like the natural numbers to the n, then you just see T to the n. You see tropical affine n space. Okay, so as I was saying, the Berkovich analytification is a completely intrinsic thing. It just depends on X, whereas the tropicalization is a finite thing where the Berkovich analytification was quite infinite, but the tropicalization depends on this extra choice of an embedding. Now, the relationship that brings these two things together is, well, first, here are two facts. So the first fact is there exists a canonical map from the analytification. It's in fact a surjective map to the tropicalization of X inside any toric variety. So given any tropicalization, any toric embedding which you can tropicalize, you get a canonical map from the analytification onto it. That's fact one. Let me just write down how you define this map. So a point of the analytification is some valuation W in the affine case. So we can send W to the composition where I take my monoid M and I include it into K adjoin M, which surjects onto K adjoin M modulo the ideal. This is the map of algebras defining this closed embedding here. And then the valuation W is a valuation on this algebra here. So I can do W to land in T. This map here is a multiplicative map, but it's not a ring, a ring or a semi-ring homomorphism in any sense. It's just a multiplicative map. This one is a ring homomorphism, and this one is a valuation, so it's a multiplicative map, which is, in addition, subadditive, but we're not going to worry about that. So the whole composition is a multiplicative map, and so it lands in Hom of monoids from M to T, and then you can check that actually it satisfies this max attained twice condition, this tropical vanishing condition, so it actually is contained in the tropicalization of X. Okay, so that's fact one. And the second fact is a theorem. Actually, the theorem is a theorem, not a fact, so I should say second fact is there exists a theorem due to Sam Payne, which says that for X quasi-projective, the analytification is actually in bijection with it. In fact, with the Berkovich topology on this, which Matt mentioned in his talks, the analytification is actually homeomorphic to the inverse limit. Let me write this. The inverse limit as you vary over all toric embeddings of X into some toric variety Z of the tropicalization of X in Z. So the inverse limit of the tropicalizations with respect to all toric embeddings gives you the analytification back. So the analytification maps to every tropicalization, and it is in fact not just mapping to all of them, it's the inverse limit of all of them. And so this theorem we take as justification for heuristically thinking of the analytification as a kind of universal tropicalization. We haven't yet said it actually is a tropicalization, but it behaves like a tropicalization. It behaves like the universal tropicalization, the one which maps to all of the others. So that's the statement that I want to explore today. Now, let me make what's going to seem like a kind of trivial observation, but is going to hopefully lead somewhere. So this is an observation about this tropically vanishing condition. So given a bunch of tropical numbers, T1 through Tn, then the sum tropically vanishes, which is to say the maximum of all these Ti is attained at least twice, or the whole thing is equal to negative infinity, if and only if the sum as I equals 1 up to n of Ti is equal to the sum for I not equal to j of Ti, and this is true for all j. So if I sum up all the Ti's, then I have to get the same result as if I sum up all but one of them. If I leave out one of my numbers from the sum, I don't change the value of the sum. So that happens if and only if, well, if you drop out any sub-maximal Ti, then clearly you're not going to change the value. And if you drop out a maximal Ti, you are going to change the value if that one that you dropped out was the only one attaining the max at that point. But if there are two simultaneously attaining the maximum, then dropping out one of them isn't going to change the value of the sum, and so you're OK. So The sum tropically vanishes if and only if this funny condition, where you can drop out any term and not change the value, is satisfied. Now, I just want to emphasize this a little bit. This tropically vanishing condition, that is a condition which makes sense only in the context of the tropical numbers being totally ordered. The tropical numbers have a total ordering, and we can talk about the maximum of a subset, and we can talk about whether or not it's attained twice. On the other hand, this condition down here is something which makes sense a little bit more generally. This makes sense if these numbers ti are in any old idempotent semiring, not necessarily a totally ordered one. So I think that this one is, in many senses, a more useful condition to use, and in particular when we try to describe tropical varieties as schemes. When we try to give the equations that define them, this is what we use rather than the tropical vanishing condition. So let me explain how that works. So given a tropical polynomial G, V trop of G, the tropical hypersurface of G. So I define this for you over there. It's the set of all monoid homomorphisms from M to the multiplicative monoid of T, such that the maximum of the terms is attained at least twice. It tropically vanishes. By this observation over on my left here, this is the solution set to the system of equations G is equal to, I'll write G sub I hat, as I varies over all the elements in what I'll call the support of G. So let me define this for you. So G is my polynomial. G I hat just means we are going to take G and delete the ith term from it. We're going to leave one term out. So a quick example. If G is x plus y plus z, then the equations are x plus y plus z is equal to x plus y is equal to x plus z and is equal to y plus z. So one polynomial G is giving us, in this case, 3 different equations, but that's OK. So the tropical hypersurface associated to this tropical polynomial G, the bending locus or corner locus, whatever you want to call it, is exactly the solution set to these equations. And these equations, they come up a lot, so we give them a name and a symbol. These are the bend equations of G, and I use a curly B of G. Or the bend relations. Okay, so these are the equations that describe the tropical hypersurface. These are equations which cut out this particular solution set. Now, in the philosophy of scheme theory, if you have an algebraic variety, that's the set of solutions to some system of equations, Grothendieck says we should take the system of equations as the fundamental geometric object which we study, and the set of solutions to that system of equations is some derived thing which we may want to look at some point. But you might want to look at the solutions with values in T or solutions with values in some other semiring in this case. So giving a system of equations whose solution set is the tropical hypersurface of G is realizing the tropical hypersurface, which previously was a polyhedral set. It's now realizing it as some kind of, in this case, affine scheme over the tropical semiring T. So coming back to our toric embedding of X, if this is given by quotient by some ideal, so X is carved out of Z by the ideal I, then I can define a scheme-theoretic tropicalization. So I've been carefully using lowercase t for the set theoretic tropicalization, and now I use an uppercase T. So the tropicalization of X inside Z is spec of so I take my monoid, which was describing the ambient space, and I change the coefficients from the field K to T, and I need some quotient of this tropical algebra here. The quotient is I apply the bend relations to every single element in the tropical ideal given by tropicalizing my classical ideal. So this is this spec of this semi-ring here. So this is a scheme over T. It's an affine scheme over T. If you don't have any experience with scheme theory over semi-rings, it's okay. Affine semi-ring schemes are just the opposite of algebras, as in the classical case. And the gluing, which I don't want to say too much about, is exactly the same in the classical case if you're in a non-affine setting. It's just given by multiplicatively inverting some elements to localize and glue patches together. So I don't want to worry anymore about the gluing. So this is a scheme over T. And since these bend relations carve out tropical hypersurfaces, it follows that the T points of this thing are exactly the set theoretic tropicalization. So this is some scheme which is refining the set theoretic tropicalization that we all know and love. Now, I want to say a few words here before I move on to doing something with this and making some interesting observations. So the first is, so this scheme theoretic tropicalization is carved out by this system of equations here, the bend relations applied to all the elements in the tropicalization of I. These systems of equations, these things are called congruences. They define quotients of semi-rings. These systems of equations of this form are very special. If you write down a general system of equations over T, the solution will look like some polyhedral complex. And in fact, any polyhedral complex can arise as the set of solutions to some system of equations. So to get things which look like balanced polyhedral complexes out, you need very special systems of equations. And we believe that the systems of equations which give you these balanced polyhedral complexes should look generally like this. And this is what Diane's talk is going to be about. So she'll go into more detail on that, I think. So the point I want to make, though, is that the systems of equations which carve out tropical varieties as schemes are very special. Now, the tropicalization, as we've seen, is more than just a set. It also has these weights. And thanks to some work of Diane and Felipe, it turns out that the scheme-theoretic tropicalization, this scheme here, actually determines all those weights. So Noah and I showed this in the case of a hypersurface, and Diane and Felipe did the general case. So the scheme-theoretic tropicalization determines the weights. Does the set-theoretic tropicalization plus weights determine the scheme? No. No, the scheme is strictly more information in at least some examples that we've worked out, thanks mostly to Felipe's hard efforts. Sorry? That is, at the moment, an open question. I believe, and I think Diane and Felipe believe, the answer is going to be yes, but that's a conjecture right now. Okay, so yeah, so Noah and me for hypersurfaces, and McLagan and Rincon in the general case. Okay, so far we don't really have an application for this scheme structure. We believe that it's going to be useful for something. I mean, these days you would be crazy to say that schemes are not useful in algebraic geometry. So surely they must have some interesting use in tropical geometry. I just have to admit, we haven't found it yet. But as Sam mentioned in his talk, they at least have contributed to noticing and understanding some things. So let me now talk about something that the scheme structure helped us notice, which I don't think we would have noticed, at least not quite so quickly, if we hadn't been thinking about these scheme structures. So this is something about valuations. So here's a fact about valuations. So given a valuation V from some ring to the tropical numbers, and two elements of this ring R, we can look at the three numbers, valuation of A, valuation of B, and the valuation of A plus B. So these are three tropical numbers. We know that a valuation is a multiplicative map, which is, in my sign conventions, which are admittedly bizarre, and so the opposite of what everybody else uses, a valuation is a multiplicative and sub-additive map. So the valuation of A plus B, in general, will be less than or equal to the valuation of A plus, in the tropical sense, meaning max, valuation of B. But the fact is, and this is an easy little exercise you can do, that of these three numbers, the max is attained at least twice. So the max of these three numbers happens at least twice. So the sum of these three numbers tropically vanishes. So the condition of being a valuation looks quite a lot like something we've seen already, tropical vanishing or bend relations. In fact, this is an if and only if. So a multiplicative map is a valuation if and only if it satisfies this condition. So being a valuation looks very much like sitting on some kind of tropical hypersurface or some kind of tropical variety, but we don't see exactly what yet. We just see that being a valuation looks like the condition of tropical vanishing for something. So this is an observation that I want to explore further. And this seemingly slightly random observation turns out to be very closely related to the relationship between the Berkovich analytification and tropicalizations. This is really at the heart of that. So now I want to come back to talking about the relationship between analytification and tropicalization. So in Payne's inverse limit theorem here, and this is the theorem that really, I think, got a lot of people thinking about the relationship between tropicalization and analytification. In this theorem here, you look and you say, we're taking the limit, the inverse limit over all toric embeddings. It'd be really nice if we could simply find some universal toric embedding. But toric varieties they're varieties. They can't get arbitrarily large, and so there isn't a universal toric embedding. So there isn't a universal toric embedding. However, you can still take the inverse limit over all of these z's here that x is being embedded in and get something. It won't be a toric variety, but it still has some structure that it turns out is enough to tropicalize in. So the limit exists as a scheme. In fact, it's a scheme which is locally of the form spec of k adjoins some monoid here. In a toric variety is something which is locally of this form, spec of k adjoins some monoid, where the monoid is a toric monoid. It's some cone of lattice points inside r to the n for some finite n. This z here, this limit, is going to be of this form, except the monoid appearing here is horrendously huge. It's some huge infinite monoid that you can put in there, which is just formally the universal thing. I'll explain exactly what that monoid is. It's not actually so ugly. I just wanted to have a bit of fun for a moment. So let me give you a different description of this universal object that you can embed in. Okay, so here's an alternative description. We have the category of K algebras, and we have the category of monoids with 0. Now, monoids with 0 means monoids, multiplicative monoids, equipped with a distinguished element which is absorbing. So some element which I call 0, such that anything times 0 is equal to 0. So for fun and to be fancy, I'm going to call this the category of F1 algebras. But if you find that language too fancy, just think of it as monoids with 0. Now, there is a forgetful functor which sends a K algebra to its underlying multiplicative monoid. It simply forgets about the additive operation on that algebra. So just its underlying multiplicative monoid. We're not throwing out the non-unit elements. It's not the group of units. It's just the multiplicative monoid of all elements. So this is a forgetful functor, and it has a left adjoint, which is a free functor, or a base change functor, which sends a monoid M to, I'll write this as K adjoin M. Strictly speaking, I have to be a little bit careful here. M is not a monoid, but a monoid with 0. And so what I do is form K adjoin M, and then I need to identify any scalar times the 0 element of M with the 0 element of this ring. But I'm going to gloss over that point. It's easier to just write K adjoin M and tell you what I mean by that. So this is a base change and scalar restriction adjunction between K algebras and F1 algebras. So when you have an adjunction, you can go around the loop, and you get a unit and a co-unit for this adjunction, if you like category theory. So the co-unit for this adjunction is the map which goes from, so we take a K algebra A, given a K algebra A, I regard it as just a multiplicative monoid, and then I hit it with this base change back to K algebras, so I form K adjoin A. And there's a map which is a surjection, it turns out, down to A. This thing K adjoin A, this is the K algebra with generators. I'll write it as XA for each A, little a in big A, and XA times XB is equal to X sub AB. So I use this notation, X sub A, rather than just writing A, to avoid confusion. So this map here is given by sending XA to A. So I can think of this map, so I usually call this the evaluation. It takes a formal K linear combination of elements of A and evaluates it to an element of A using the arithmetic of A. So this map here, you have it for any algebra. This happens to be the co-unit of this adjunction. You don't need to know any category theory from this point on. I just thought I'd use that word in case you recognize what's going on here. Now, this evaluation map is going to turn out to be very closely related to that observation I made about valuations. I'll come back to that in a few minutes. Let me just say how we get this universal embedding. So if X is spec A, and this gives a universal embedding, meaning universal among embeddings into things which are locally of the form K adjoin some monoid. It gives a universal embedding, which I'll just write as X into X hat. So X is spec A, and X hat is spec of K adjoin A, and the closed embedding is given by, on the level of algebras, the evaluation map. Okay, the universal property is the following. Given a toric embedding X into Z, there exists a unique morphism from X hat to Z such that the diagram commutes. So this universal embedding that I constructed from the co-unit of the adjunction between F1 and K algebras, this constructs for me an embedding into something which is of the form that I can tropicalize in it, and it's universal among all the embeddings into toric varieties. Moreover, it's in fact universal among embeddings into things locally of the form spec of K adjoin some monoid. So, moreover, it's an easy calculation that the limit over all toric embeddings actually constructs this thing. So it's not a toric variety, but it's the inverse limit of all the toric varieties that X embeds into. It's the universal toric embedding. Yeah? Yeah, so when I say toric embedding here, yeah, toric monoid. And the thing you construct in the limit isn't a toric monoid. It's the monoid that describes X hat. Yeah, this proposition is exactly a formal property of the adjunction. It's just re-expressing the universal property of that adjunction. Nothing. Sorry, this part is the universal property of the adjunction. This part is a calculation, but an easy one.
But there's this one thing that for toric varieties you only look at monoids, which
yeah. Yeah, so you can build the whole of X hat even by only looking at affine toric varieties. Yeah, that's a calculation. It's pretty straightforward and trivial. Yeah, I should have said that. Yeah, I'm trying to avoid using a whole bunch of F1 language, which would have everybody's heads spinning. Okay, so now back at the very beginning, when I was defining tropicalization and introducing my notation, the reason I did it that way was so that I could make the following point right now, which is that when you tropicalize, you don't have to tropicalize inside a GM to the n, a torus. You don't have to tropicalize inside an affine space. You don't have to necessarily tropicalize inside something which is a toric variety. You can tropicalize inside anything which is locally of the form spec of K adjoin some monoid. It's just being in the image of this base change. You need something which was an F1 algebra base changed to K. And if you're embedded in something of this form, then you can tropicalize. And that's the only thing that you need to tropicalize, at least on an affine patch. It turns out that with the technology I have at hand, when you want to globalize this, I know how to do it when these monoids are all integral. I don't quite know how to do it when they're not integral. I don't know how to do the gluing. Oliver thinks that's okay, though. So we can discuss more of that later. I think that is just a kind of technical restriction, which I don't want to emphasize right now. OK, but so the point is that, in particular, this x hat here is a spec of k adjoins some monoid. It's something we can tropicalize in. So what happens when we tropicalize x inside this universal embedding? So this is the universal embedding. Its tropicalization should be the universal tropicalization. And now we're getting a hint here that this is going to be related to the Berkovich analytification. So let's see how this fits with that observation about valuations. Well, if you play with this evaluation map, it's not too hard to see the following lemma. The kernel of the evaluation map is spanned by the following guys. We have things of the form x sub lambda a minus lambda x sub a, where a is an element of my algebra A, and lambda is an element of the ground field. And we have things of the form x sub a plus x sub b plus x sub a plus b for a and b elements of the algebra A. I think those are all pluses there. OK, so that's a pretty easy thing to show. But I'm going to be interested in tropicalizing this ideal and then applying the bend relations to it. So what I'm really interested in is the whole ideal and all of the bend relations that I get from all of the elements in this ideal. And it's not necessarily true that just taking some generators of the ideal is enough to give you all the bend relations that are going to appear. This is a kind of an irritation that we're dealing with. It already shows up set theoretically in the concept of a tropical basis. But now it's even worse because we're not just trying to get the right solution set, we're trying to get the whole correct system of equations here. I think I can use plus or minus there. Either one will generate the ideal. No, this is the kernel of the evaluation. It's over K. Oh, sorry. I stand corrected. It should be a minus there. Yeah. Yeah. The other thing I could do is use this relation to stick the minus into the denominator there. Yeah, OK. Yeah, so these elements generate in fact, they span the kernel. And then what's a little bit stronger is that the bend relations of the coefficient-wise valuations of these guys generate the whole system of equations, bend relations of the tropicalization, of the kernel of the evaluation map. So this is the full system of equations that describes the tropicalization. And I'm saying that it's enough to take the bend relations associated to this much smaller system of generators of this ideal. So that's an important technical thing there. Okay, so this relation here is supposed to look exactly like, or is supposed to be very reminiscent of that condition that I wrote down for evaluation in terms of tropical vanishing. The bend relations, you should think of x sub a as being the generic valuation of a. X sub b is going to be the generic valuation of b when I tropicalize, and x sub a plus b is going to be the generic valuation of of a plus b. So the bend relations coming from these guys are going to give us exactly this subadditivity condition that I wrote down for valuations. So the tropicalization of x inside x hat, where x is spec A, is carved out from spec of T adjoin A by the bend relations of, I have to evaluate the coefficients. So this is x sub lambda A plus the valuation of lambda x sub A. And the bend relations of a binomial turn out to be just this monomial is equal to this one. And so that relation is expressing compatibility with the valuation on the ground field K. And the bend relations of, coming from these guys, x sub A plus x sub B. Now I really can write a plus x sub A plus b, and these bend relations are expressing exactly the subadditivity. So I can state a theorem now. And this is so I'm going to write down several parts to this theorem. Some of them appeared in the first paper that Noah and I wrote. Some of them also appeared more or less simultaneously in Andrew McPherson's thesis. And then some of the things I'm going to write down only appeared in the second paper that Noah and I wrote. So I'll explain the structure here as we go. So this universal tropicalization, we already said this is a scheme over T whose T points give the Berkovich analytification as a set. In fact, if you look at Andrew's thesis, you can see how to get the Berkovich analytification's topology from this sort of stuff. So you can also recover the Berkovich topology. So that's the first part. The second part is there exists a canonical map to any other tropicalization. So And this gives the map from the analytification to the set theoretic tropicalization of x and z on the level of t points. So given any other scheme theoretic tropicalization, I can take, I have a map from the universal tropicalization, the universal scheme theoretic tropicalization to this other scheme theoretic tropicalization. When I pass to t points, this universal guy becomes the analytification, and the other guy becomes the usual set theoretic tropicalization for that embedding. And this canonical map expressing this as the universal tropicalization reduces to the map that we already know about from the analytification to a particular tropicalization. We can say a little more. So morphisms from a T algebra S, from spec of a T algebra S into the universal tropicalization. These are the same thing as valuations on the structure sheaf of X with values in S. So this is expressing this universal tropicalization as the moduli space of valuations on the structure sheaf of X. The Berkovich analytification you can think of as the set of all real valuations on X. And what I'm saying here is that it's not just the set of all valuations, it's actually an algebraic moduli space of valuations. So we strengthen that statement a little bit in a sense. And then the last part is a scheme theoretic version of Payne's inverse limit theorem, which says that the tropicalization of X inside X hat is isomorphic as a scheme to the limit over all toric embeddings of the scheme theoretic tropicalization of X inside Z. So this is the scheme theoretic version of Sam Payne's inverse limit theorem. So now let me try to say a little bit about who did what here. So in Andrew's thesis and in the first paper that Noah and I wrote, we produced this universal tropicalization as a scheme, but not as a tropicalization. We just, Noah and I wrote down generators and relations, and Andrew used some very nice universal properties to produce a scheme. But we didn't know at the time that it was actually a tropicalization of something. So we had the existence of this scheme. In the second paper that Noah and I wrote, we looked at this, this map to any other tropicalization and saw that it has this universal property, and we realized that it actually is the tropicalization of the universal embedding. This universal property here was in Andrew's thesis, I believe, and in both of the papers that Noah and I wrote. And the inverse limit theorem here was in the second paper that Noah and I wrote. But I think Andrew had, did you have this or no? Okay, but Andrew had some similar things. Okay, so that's more or less who did what here. And I'm just about out of time, so the last thing I'll say is the next thing to do here is understand how skeleta arising from semi-stable models appear as closed subschemes of the Berkovich analytification as a scheme over T. So that's something that I think Andrew is thinking about and Noah and I are thinking about also. And so that hasn't been done yet, but we're thinking about that. And I'll finish there. Thank you very much.